This is video 6 of Unit 7. In this video, we will take a closer look at vapor pressure and see how it relates to temperature. Remember, vapor pressure applies usually to liquids. Now, we've seen a graph like this before, back in the gases chapter, and this is a little bell curve showing you the distribution of molecules at different temperatures. So this is usually shown as a bell curve because there's such a big number of particles in any sample of gas that you have to treat them as a huge population rather than individual molecules. And this bell curve shows that most of the molecules, if you take a look at this blue curve, most of the molecules have an average amount of energy. Some have a low amount of energy, and some have a high amount of energy. That would be out here. Now, what we see here as the temperature increases, so real quick, vapor pressure, recall, is the pressure created by the vapor of a liquid phase. So if you let a liquid sit in a closed container, a lot of the liquid would go into the vapor phase, and this will create some pressure. And we can actually measure that pressure. And it's dependent on the strength of the intermolecular attractions. If these are weak, then you'll have a high vapor pressure. If they are strong, then you have a low vapor pressure. So here it says, at any temperature, some molecules, a portion of the molecules in a liquid have enough energy to escape, and these are the ones that go into the vapor phase. And what happens really is you see these arrows going up and going down, that this process actually occurs simultaneously. There's new molecules evaporating, and there's molecules also condensing at the same rate. So the pressure becomes constant, is the idea here. Now, you can see that at a lower temperature, which is represented by the blue line here, you have a fraction of molecules, that would be this fraction here, that are able to escape into the gas phase, that have enough kinetic energy to be in the gas phase. But if you increase the temperature, every time you increase the temperature, this bell curve stretches to the right. And so at a higher temperature, which is represented by the red, now you have a larger amount of molecules. It actually includes all the molecules below it. Notice you have more molecules now able to escape, which means the pressure in here has gone up. The vapor pressure will go up. And then if you have a third temperature that's even higher, then this can be drawn out even further, like so. You'll have a large number of molecules having enough energy to escape. So this kind of shows you as you increase the temperature, the vapor pressure increases. And that should make sense, but you can actually graph this. The more important graph to look at will be something like this. We've created vapor pressure curves for different substances, and this is a curve, or this is a graph that plots temperature on the x-axis versus vapor pressure on the y-axis. You'll notice temperature is in Celsius, and then the vapor pressure is in torr. So what you see here is 4 curves. We have 4 curves. Water actually has is the one we're used to. So you take a look at this is the water curve. This is ethyl alcohol. This is an alcohol, type of alcohol. And out here we have ethylene glycol, which is actually a very important compound used in not refrigerants, but as antifreeze for car engines. Now, what you see here is as the temperature goes up, the pressure goes up, but it's not linear. It's actually an exponential relationship. So it's exponential. So as you increase the temperature, it rises slowly at first, but then it really shoots up. And this is true for any one of these. It's essentially an exponential curve. Now, what you'll find, so for example, at 40 degrees Celsius, water's vapor pressure is pretty low compared to it being 80 degrees Celsius. If you just increase it by 40 degrees, notice the water vapor pressure really shoots up to about maybe 350 or so. And there comes a point where the vapor pressure is matched, which is 760, which is the pressure outside. Now, for these 4 compounds, what you'll see is that the one that has the strongest intermolecular forces is ethylene glycol here. We know that because at a given temperature, say at 60 degrees Celsius, it has the lowest vapor pressure, close to 0. Water at 60 degrees Celsius has a considerable vapor pressure. The vapor pressure of ethyl alcohol at that same temperature is, about 300 maybe, which means a little above 300, which means ethyl alcohol actually has weaker intermolecular forces. So this is weaker, and ethylene glycol has stronger intermolecular forces. That's the idea here. The weakest of all, of course, then is the dimethyl ether. notice that at 60 degrees Celsius, its vapor pressure is just through the roof. If you keep, doing this, then it'll be extremely, extremely high. Essentially, all the ethyl ether is vaporized. There is no liquid left. That's the idea. And so we're going to focus on this number right here. I would like to show you that number. So it's an exponential curve, and you can see it from here. You can actually tell which compounds have stronger, which compounds have weaker intermolecular forces. Now, here it says the boiling point of a liquid is the temperature at which the vapor pressure of that liquid equals the atmospheric pressure. So notice water. When you reach a temperature of 100 for water, notice that the vapor pressure at that point is 760. Now that's how you define the boiling point of water. It's the temperature at which the vapor pressure of water equals atmospheric pressure, which happens at 760, which is also 1 atmosphere. Remember, 760 is 1 ATM. That's why under regular conditions, 1 atmosphere, the boiling point of water is 100. So from here we can actually find the boiling point of ethyl alcohol. The boiling point of ethyl alcohol, if you come down, it reaches 760 at a temperature just below 80, which is actually 78.3 degrees Celsius. That is the boiling point of ethanol. The boiling point of diethyl ether is quite a bit lower, 34.6, and if you take a look, that matches. So that's how we define a boiling point. Now here it says the normal boiling point. The word normal means at 1 atmosphere is the temperature at which its boiling point, its vapor pressure is 760 torr. So obviously, because what will happen is if the atmospheric pressure changes, then the boiling point changes. And we'll talk about this in just a little bit. Now, this is why, since the boiling point changes under different pressure conditions, this is why the boiling point is lower at higher elevations. So if you go up a mountain, the boiling point will be lower. So here we have a graph that shows you the different boiling points in Fahrenheit in this case. Remember, a regular boiling point is 212 Fahrenheit. So if you're at sea level, and Death Valley is actually a little bit below sea level, but it's roughly close to sea level, your boiling point will be 212. If you're up in Denver, your boiling point will actually be about 102 Fahrenheit, so a few degrees below, usually maybe 95 Celsius, 96 Celsius. And then if you are up in Peru, one of the high mountain peaks of Peru, your boiling point is close to 182 Fahrenheit, so quite a bit of a difference. And if you are on Mount Everest, the highest point on Earth, your boiling point is only 160 Fahrenheit, which is pretty impressive. And that's a full 50 degrees Fahrenheit below the regular boiling point, which is a good 20 degrees or so Celsius below. So you can actually see experiments done where folks try to boil water on Mount Everest, and the higher they go, the lower the temperature of the boiling point is. And this is also how you can boil water without heating it, without being heated. You simply drop the pressure above the water, and it will boil without being heated. And we'll show you this in the next curve. So this is the relationship between temperature and pressure, vapor pressure. Now there is an equation for this. The equation relates the vapor pressures to the boiling points. It's called the Clausius-Clapeyron Equation. And you can actually determine the vapor pressures at different temperatures. What you have here, it's a pretty complex equation. We're not going to use it too much, but we may pull it up here and there. It uses the natural log. There's a button on your calculator called a natural log, but this is essentially a function from math. It's related to exponential decay and exponential growth. That's because our graph is an exponential graph. So what you have is the two pressures, P2 over P1. So say your vapor pressure at a higher temperature versus vapor pressure at the regular temperature is equal to the negative of the heat of vaporization. This is a constant. How much heat it takes to vaporize a substance. We've seen this term. Divided by the R constant. Now the R constant here is the gas constant, but you have to use the R constant that's consistent with energy, which is the joules of energy. So you have to actually use this 3.14, not the 0.0821. And then you have the two temperatures here. You have the original temperature and then the new temperature. So say if you want to know the vapor pressure of water at 50 degrees Celsius, what you'll do, and this has to be absolute temperature, you'll put 50 Celsius in here, except it has to be in Kelvin. You'll put room temperature here, and then you'll put your heat of vaporization of water, that 40.79 number in here, and then if you know the vapor pressure of the first, then you can find out the vapor pressure of the second. That's the idea. Or you can find the ratio of the two vapor pressures. So you can actually use this equation to determine the vapor pressures of different temperatures, and that's the idea. Okay, now we're going to take a look at the phase diagram, or we're going to look at multiple phase diagrams. In fact, let's go ahead and do this. Let's devote a whole separate video to this, video 7, to the phase diagram. So we'll continue this in video 7.